Harvard scientist has just shattered the silence on one of the most mind-blowing cosmic mysteries unfolding right now in our solar system. Imagine this: an interstellar visitor named 3I/ATLAS hurtling through space at a blistering 130,000 miles per hour is shedding metallic alloys that defy everything we know about earthly or even solar system materials. That's right, you read that correctly. Fresh NASA data, backed by observations from the Very Large Telescope and the James Webb Space Telescope, confirms atomized nickel streaming from its coma, but with virtually zero iron detected alongside it. The chemistry simply doesn't add up, and Harvard's renowned astrophysicist Avi Loeb is raising the alarm louder than ever. If these metals aren't the result of some natural cosmic process, what could that possibly mean for humanity's place in the vast universe? Some experts are chalking it up to a freakish stellar forge, while others are whispering about the possibility of something engineered, perhaps even artificial. No one could have predicted this twist, and it's shaking the foundations of astronomy. So what's truly racing toward us at that insane speed, and why does it matter? Stick with me through this deep dive, because the answers could completely upend everything we thought we knew about the cosmos. By the end, you'll see why this isn't just another space rock. It's a potential game changer for science and our understanding of life beyond Earth. Picture this interstellar intruder not sneaking in quietly, but blazing into our view like a cosmic fireball from the infinite darkness between stars. On July 1st, 2025, the Atlas survey team, operating from their advanced telescope in Chile, first spotted 3I/Atlas as a faint, incredibly fast-moving speck against the night sky. Right from the start, the data screamed anomaly. This wasn't your typical comet looping lazily around the sun on a predictable path. No, its trajectory was hyperbolic, with an eccentricity clocking in at a staggering 6.141, meaning it's not bound by our sun's gravity at all. This is no repeat visitor. It's a one-and-done interloper from deep interstellar space, zooming too fast for the sun to ever reel it back in. Astronomers quickly dug into archival images and traced it back to sightings as early as June 14, 2025. The more they crunched the numbers, the clearer the picture became. 3I/ATLAS originated far beyond our planetary neighborhood, possibly from the bustling galactic center or even another star system entirely. By the time of discovery, it was already cruising inside Jupiter's orbit, gearing up for a dramatic slingshot around the sun before vanishing back into the void forever. Its relative velocity to the sun, a jaw-dropping 58 kilometers per second, placing it in an elite category of cosmic speed demons. To put that in perspective, that's over 130,000 miles per hour, faster than any human-made spacecraft has ever traveled. This isn't merely a tumbling rock. It's a genuine messenger from the stars, carrying secrets from light years away, and it's on a path that ensures it'll never return. If discoveries like this set your imagination on fire and leave you craving more, hit that subscribe button right now and turn on notifications. We're just scratching the surface here, and trust me, the story of 3I/ATLAS only gets stranger from here. You won't want to miss the revelations waiting at the end. The spectral lines for nickel began popping up almost immediately after 3I/ATLAS dipped inside Jupiter's orbit. But the real shocker wasn't the nickel itself. It was the glaring absence of its usual cosmic companion, iron. In every meteorite, comet, or asteroid we've ever analyzed from our solar system, nickel and iron are inseparable twins, forged in the fiery hearts of dying stars and released together when celestial bodies heat up near the sun. Yet here we are with data from the Very Large Telescope, VLT, in Chile showing a robust nickel signal, clocking in at about 4.6 grams per second, evaporating from the comet's coma by late August 2025. But not a whisper of iron. That's not just unusual, it's unprecedented, like discovering a pristine gold nugget without any trace of the impurities that always tag along in nature. Harvard astrophysicist Avi Loeb was among the first to spotlight this enigma, questioning not only the abundance of nickel, but how on Earth, or rather off Earth, you could possibly separate it from iron in the vacuum of space. In laboratories here on our planet, isolating these elements requires sophisticated industrial techniques involving extreme temperatures and chemical processes. Out in the cosmos, it's virtually unheard of. Loeb describes this nickel without iron signature as a fingerprint that doesn't match any natural database we have. The data supports his concern. In typical solar system comets, the nickel-to-iron ratio sits comfortably around 1 to 15, a balanced partnership honed over billions of years. But for 3I/ATLAS, that ratio is skewed beyond recognition. Iron is simply MIA. So what are we dealing with here? Could there be some undiscovered natural mechanism in the depths of space that brews pure nickel vapor while sidelining iron? Or, as some daring voices suggest, are we witnessing evidence of engineering, a deliberate design meant to catch our attention? This has sparked heated debates in scientific circles, with some calling it the first tangible chemical hint that 3I/ATLAS might be more than a mere rock. What do you think, viewers? Is this Mother Nature pulling off her most bizarre trick yet? Or is there something more intentional at play? Drop your theories in the comments below and keep watching because we're about to peel back even weirder layers that could flip your perspective upside down. Adding fuel to this interstellar fire, the James Webb Space Telescope, JWST, has delivered infrared spectroscopy data that's nothing short of revolutionary, revealing carbon dioxide as the undisputed king of 3I/ATLAS's volatile cocktail. The observations, conducted by teams using the most advanced instruments ever trained on an interstellar object, pegged the carbon dioxide to water ratio at an astonishing 8 to 1, the highest ever documented for any comet, whether from our solar system or beyond. To give you a sense of how extreme this is, most comets in our neighborhood boast carbon dioxide levels around a modest 4% of their total volatiles. But 3I/ATLAS, it's like a CO2 factory on steroids, with production rates soaring to 129 kilograms of carbon dioxide per second against a meager 6.66 kilograms of water vapor. And it's not stopping there. Traces of carbon monoxide, carbonyl sulfide, and even cyanide have been detected in the mix. But nothing rivals the CO2 dominance. These findings held firm across multiple JWST sessions as the comet barreled closer to the Sun, with perihelion slated for October 30th, 2025, at about 1.4 astronomical units. This chemistry flies in the face of established models for comet formation, which predict a more balanced blend of ices shaped by the gentle conditions of distant protoplanetary disks. Some researchers propose that this could be the scar tissue from billions of years of cosmic ray bombardment during its epic journey through interstellar space, etching away other volatiles and leaving CO2 to reign supreme. Others speculate it hints at exotic birth conditions in its original star system, perhaps near a carbon-rich giant or in a polluted nebula. But here's the burning question that's keeping astronomers up at night. Does this overwhelming CO2 surge point to nature's extremes, pushing the boundaries of what's possible in astrophysics? Or could it be a subtle sign of something engineered, a chemical beacon designed to stand out? What's your gut feeling? Pure cosmic coincidence or a crafted clue? Share in the comments and don't click away yet. We're connecting these dots to historical patterns that might just blow the lid off this mystery. Flash back to late 2017, when astronomers worldwide were left reeling by the arrival of the first confirmed interstellar object, 1I/Oumuamua. This enigmatic wanderer entered our solar system from above the ecliptic plane, clocking a relative speed of about 26 kilometers per second to the Sun. At first glance, it resembled a rocky asteroid, but its antics soon shattered that illusion. As it swung closest to the Sun, Oumuamua exhibited a slight but undeniable non-gravitational acceleration, speeding up without any visible cause. The kicker? No detectable outgassing, no dusty tail, no gaseous coma, hallmarks of every accelerating comet we've ever observed. Comets typically spew vapor and particles when heated, creating a visible trail. But Oumuamua left zilch. Its light curve painted a picture of a bizarre shape, potentially 10 times longer than wide, tumbling every 8 hours, modeled as either a cigar-like elongated body or a pancake-thin disk, defying natural formations in our asteroid belt. Explanations range from solar radiation pressure, which would demand an impossibly low density, to exotic hydrogen ice outgassing or fractal dust clouds, but none nailed all the data points. The media frenzy was instantaneous, with headlines screaming about alien probes and extraterrestrial tech. Enter Avi Loeb, the Harvard astrophysicist, who boldly stepped forward, positing that Oumuamua's peculiarities, its acceleration and shape, might indicate artificial origins. He likened the non-gravitational thrust to that of a solar sail, a hypothetical ultra-thin sheet harnessing starlight for propulsion. While the mainstream astronomical community countered with natural hypotheses, Loeb held his ground through interviews, opinion pieces, and his best-selling book, Extraterrestrial, The First Sign of Intelligent Life Beyond Earth. What lingered wasn't just the speed up, it was Oumuamua's refusal to fit any category: no tail, no standard comet chemistry, no precedent for its motion or form. It slipped out of the solar system before deeper probes could be launched, leaving telescopes scanning in vain for follow-ups. The enigma only intensified. If one interstellar guest could so thoroughly upend expectations, what other oddities lurk in the void? Loeb's audacity in challenging norms positioned him as a key figure, emphasizing that science must pursue evidence, no matter how outlandish. This mindset primed him for 3I/ATLAS's arrival, where he's again urging us to consider unconventional ideas. A pattern emerges: our solar system as a galactic crossroads, occasionally hosting visitors that bend the rules. If Oumuamua was the opener, 3I/ATLAS is the sequel that's cranking up the intrigue. Hang tight, we're linking this to ancient human encounters with sky-fallen metals that echo today's puzzles. Long before modern telescopes pierced the veil of space or spectrographs decoded cosmic light, humanity was already attuned to the allure of metals plummeting from the heavens. In ancient Egypt, iron wasn't mundane or dug from the ground. It was a divine gift, rare and imbued with otherworldly power. The earliest clues date back over 5,000 years to the Gersa Cemetery, where archaeologists unearthed tiny iron beads, hammered thin and fashioned into tubes, nestled among gold and precious gems. Advanced modern tests reveal these beads boast around 30% nickel content, far exceeding anything from terrestrial smelting, along with cobalt traces and exotic elements like germanium, the telltale marks of meteoritic iron. This celestial signature set it apart, a material born in the explosive deaths of stars and delivered via fiery atmospheric entry. The saga continues into the 14th century BCE with King Tutankhamun's tomb, where a stunning iron dagger with a golden hilt lay sealed for millennia. For years, its source puzzled experts, but X-ray fluorescence analysis cracked the code. 11% nickel, a sprinkle of cobalt, and a crystalline Wittgenstein pattern, unique interlocking bands that form only through eons of slow cooling in space's vacuum, impossible to replicate in earthly forges. Crafted at temperatures below 950 degrees Celsius to preserve this delicate structure, the dagger wasn't just functional, it was a symbol of pharaonic might, outvaluing gold because of its scarcity and stellar origins. This phenomenon wasn't isolated to Egypt. Bronze Age artisans across Turkey, Syria, and China forged tools from similar sky iron, with every tested artifact showing the same high nickel, high cobalt profile unmatched by local ores. The metal's resilience and heavenly descent made it an emblem of authority. Egyptians even coined the term Bia and Pet, meaning iron of the sky. Contrast this with earthbound iron, which tops out at 4% nickel, while meteorites routinely hit 5 to 30% or more, featuring kamacite and taenite faces sculpted by cosmic conditions over millions of years. These ancient smiths, oblivious to supernovae or planetary accretion, intuitively grasp the extraordinary in these fallen treasures. Their relics aren't mere artifacts, they're humanity's primordial ledger of fascination with extraterrestrial materials. Fast forward to today, and the same queries: what is this substance, and whence did it hail, resonate as scientists grapple with three I/ATLAS's alloys. History teaches us that the boundary between natural marvel and potential artifact has always been hazy, especially when the sky delivers enigmas that challenge our worldview. If ancient sky irons sparked myths of gods, imagine what 3I/ATLAS's chemistry might ignite in our era. Keep watching. The stakes are about to skyrocket. If 3I/ATLAS turns out to be just another quirky comet, its tail might fade into obscure journal entries. But the nickel anomaly, the iron void, and that unprecedented CO2 overload aren't minor footnotes. They're seismic shifts forcing a reevaluation of cosmic possibilities. Astronomers are poring over data that shatters established patterns, with this real-time intruder in our solar system bearing compounds unseen in such combos before. For generations, comets and meteorites have served as litmus tests for our grasp of universal chemistry, but this one is rewriting the script. The readings from VLT and JWST aren't merely record breakers, they're rule breakers, challenging the core tenets of how matter assembles in the stars. At stake is more than a textbook revision, it's the bedrock of our cosmic narrative. Should 3I/ATLAS prove naturally formed, it implies the galaxy harbors forges crafting materials in wildly innovative ways we've yet to fathom. But if those chemical fingerprints hint at engineering, the ramifications explode outward. We're potentially not alone, and this could be a deliberate cosmic postcard from intelligent life. This transcends one object. It's about matter as a medium for messages, eclipsing radio signals in durability and intrigue. Each fresh observation, every puzzling spectrum, adds to a mosaic that might affirm extreme nature or unveil extraterrestrial intent. If you're hooked and the questions are mounting, know you're in good company. The global scientific community is abuzz. The quest for clarity is ramping up, with upcoming data drops poised to sway the debate. Want to be front row for the next bombshell? Subscribe now and join the conversation in the comments. The breakthrough that alters everything could drop any day, and you won't want to miss it. Kilonovae stand as some of the universe's most cataclysmic spectacles, forging elements in manners no ordinary star could dream of. When neutron stars, the ultra-dense remnants of massive stellar collapses, spiral into a merger, the ensuing blast scatters heavy atoms galaxy-wide, like shrapnel from nature's ultimate forge. In 2017, this drama unfolded live. The gravitational wave event GW 170817, snagged by LIGO and Virgo, bloomed into a visible kilonova flash. Telescopes like VLT soon spotted strontium's signature in the glow, the first concrete evidence that these collisions birth heavy elements via the R process, a frantic neutron barrage building atoms beyond iron in mere seconds. Nickel emerges in this mayhem, with the R process stacking neutrons onto iron nuclei, yielding isotopes that decay and fuel the afterglow. Nickel to iron ratios hinge on neutron flux, expansion speed, and ejecta escape. Some models forecast nickel-rich, iron-poor zones in the debris. Unlike the methodical metals of red giants, these are blitz-forged in seconds, then chilled over eons as fragments drift. This pathway offers a plausible natural origin for 3I/ATLAS's quirks. If birthed from kilonova fallout, it might inherit a chemical brew alien to our solar system. The iron absence beside nickel surplus aligns with certain ER process simulations, and GW 170817's strontium lines bolster kilonova as odd alloy factories. The event's ferocity enables such imbalances where supernovae stick to predictable ratios. Astronomers are cross-checking 3I/ATLAS's metrics against these models. The stretch is there, but feasible. Simulations depict nickel-heavy clumps in merger tails, cooling into nomadic dust grains. If 3I/ATLAS coalesced from such, it bears a fingerprint foreign to local bodies. Even its CO2 spike could tie in. Our process ejecta, zapped by cosmic rays over billions of years, might accrue volatile sheaths unveiled near stars. No need for design here, just nature's raw fury, colliding the densest entities and spewing world-building blocks. Yet for 3I/ATLAS's extremes, it'd be a rare gem, a merger heart survivor traversing galaxies to grace us. Spectacularly natural, it slims origins to astrophysics' wildest crucibles, reminding us the cosmos thrives on surprises. Supernovae don't always detonate in tidy spheres. Some erupt in chaotic, asymmetric blasts, hurling elements unevenly across space. Take the W49b remnant, iron clusters at the core, while nickel jets outward along axes. This lopsidedness rewrites metal dispersion rules in core collapse supernovae, segregating elements into distinct pockets. Outer layers flee first, but inner iron-nickel zones mix erratically. If the collapse is uneven, explosions direct flows, trapping iron in knots as nickel escapes plumes. Chandra and NuStar X-ray maps confirm this in W49b, with nickel jets far from iron hubs. Shockwave geometry drives it. Uneven cores spawn directional plumes, ferrying select elements. For 3I/ATLAS, this posits another natural avenue. If from asymmetric supernova debris, it could start as near-pure nickel chunk, iron left behind. Millennia later, that shard cools, condenses, and roams until stellar nudges send it our way. Element clumping in remnants like W49b provides observable proof nature craft's skewed ratios. Modern models incorporate asymmetries, showing minor collapse variances yield major outflows. This isn't speculation, it's witnessed cosmic mechanics. The universe boasts multiple strange alloy recipes, Colonovae one, asymmetric supernovae another, both eclipsing earthly norms. With these forges viable, 3I/ATLAS's debate pivots, cosmic violence over design. Odds are long for snaring such a fragment, but the cosmos delivers rarities routinely. W49b underscores even outlandish signatures can stem from a star's messy demise, urging us to weigh natural extremes before leaping to artifacts. Avi Loeb doesn't view 3I/ATLAS's metal quirks in isolation. He spots a statistical red flag in its path that's impossible to dismiss. Crunching the trajectory data, he calculated a minuscule 0.005% probability that a random interstellar object would skim so closely past Venus, Mars, and Jupiter in one flyby, like acing 15 consecutive coin flips. For Loeb, this isn't mere luck. It's a trajectory that smacks of purpose. His team factored planetary positions at arrival, closest approach longitudes, and chance alignments. Each like a roulette slot, the combo vanishingly rare. Beyond passes, the path's near-flat 5-degree tilt to the ecliptic, yet retrograde motion, lets it survey inner worlds efficiently. Timing adds suspicion. Perihelion opposite Earth, minimizing observation when brightest. If evading detection was the goal, it's spot on. Critics cite the vast universe's penchant for oddities, but Loeb retorts, with only 3 interstellar objects spotted, 1 in 20,000 odds imply either underestimated visitor rates or something unique here. Layering missing iron, nickel excess, and this path, he urges treating artificial hypotheses seriously, not claiming probe status, but demanding scrutiny. If intentional 3I/ATLAS becomes messenger scout, reshaping galactic views, this fuels ongoing discourse, with Loeb advocating deeper dives into every orbital nuance. Because if data holds and alloys suggest craft, this transcends Comet. It's a galactic clue, spotlighting our spot in the cosmos. In 1977, NASA hurled Voyager 1 and 2 into the abyss, each bearing a golden record, a copper-plated time capsule etched with Earth's essence. Music, multilingual greetings, scientific schematics, all encased for interstellar eternity. Carl Sagan, the visionary behind it, dubbed it a message in a bottle, a hopeful gesture that, eons hence, some finder might glimpse our 20th century soul. Not mere experiment, it affirmed faith in matter's enduring communicative power across cosmic gulfs. Now 3I/ATLAS evokes striking parallels, an ancient object freighted with anomalous metals and volatiles. Nickel sands iron, CO2 supremacy, a precision path, That begged the question, could this be another's time capsule? Chemistry as codec? Rather than vinyl grooves, perhaps elemental ratios, mineral lattices, isotopic sequences encode data, resilient against space's rigors. Sagan noted launching such speaks volumes of planetary hope. If 3I/ATLAS's traits are deliberate, it's no passive rock. It's a courier bearing another's chronicle in atomic form. This isn't far-fetched. We've done it, entrusting matter with meaning for the long haul. Now the query flips, are we decoding nature or a stellar archive? If capsule, every anomaly is datum. The next hunt seeks patterns in ratios, isotopes, orbits. Spotting one means we're not observing a transient. We're deciphering a metallic missive, eons in transit. That pivot redefines everything, from solitude to shared galactic tales. Envision a communique etched not in waves or beams, but atoms themselves. That's the paradigm some theorists now probe amid 3I/ATLAS's data deluge. Traditional city scans skies for radio bursts or laser pulses. But what if signals lurk in isotopic tapestries? Elemental blueprints nature shuns. 3I/ATLAS's isotopes already intrigue, deviating from expected norms. Isotopic encoding mirrors earthly feats. Nuclear forensics traces origins via uranium-plutonium mixes. DNA codes life in base quartets. Advanced societies might wield the periodic table as QR code, sculpting isotopic patterns unnatural by accident. Earth labs tailor alloys, tweak isotopes for tech, extrapolate to stellar scales, and civilizations could imprint messages in durable matter, immune to interference, billion-year shelf life. Spectrographic halls from 3I/ATLAS now undergo isotopic scrutiny. Do they echo neutron mergers or flaunt design deviations? This quest for order amid entropy, a hallmark of intent over chance. Affirmative? We're beholding a bespoke missive, awaited across epochs. Negative? The riddle deepens, blurring artifact accident lines. Either outcome revolutionizes cosmic dialogue, proving the universe's whispers can be solid, eternal. On July 1, 2025, astronomers cemented 3I/ATLAS as the third known interstellar interloper, streaking at 130,000 miles per hour. VLT Spectra unveiled potent nickel-sans iron, a solar system stranger. JWST clocked record 8-to-1 CO2 water plus cyanide spikes. These signatures defy comet norms, with colonovae in asymmetric supernovae as natural contenders, yet gaps persist. Trajectory odds at 0.005% prompt Loeb's engineered origin call, echoing Oumuamua and ancient meteoric irons. No Earth lab replicates its alloys yet. Probes continue, but data already reshapes cosmic views, demanding we entertain once fringe ideas. Humanity's universal role evolves, grounded in irrefutable evidence.